congruence modulo 24, and it involves a summation of a lot of large numbers. Now we are looking for a solution in what they call the reduced residue system, I believe. And of course, when you divide by 24, you can leave a remainder of 0. I'll just write out a few of them here. 1, 2, and then we'll do our usual ellipse here. And the largest possible remainder when you divide any number by 24 is certainly 23. So let me write that down. So we are looking for one of these 24 solutions. A number that's a multiple of 24 would be congruent to 0 mod 24. Okay, now just to give you an idea of the computational nastiness of this, it would be very time consuming. The very first prime that fits this category would be 601. 601 is the first prime after 600. And so we would be looking at 601 squared. Now, if you were to do that by hand, you could, but then you would have to divide it by 24, right, and see what the remainder was. And that's just one of the primes. Now, the very last prime in this list, I think, folks, is 839, and I may be wrong about that. I think I verified that before this video. And I'm leaving out a lot, of course. So the very last one would be 839 squared. And again, I'm clearly not listing all the possibilities here, but just giving you a feel for what the computational burden would be right here. So this is 839 squared. All right. Now again, you just to square this number out and then square this number out, add them together and divide by 24 would be a burden, right? So we don't want to do that. Possible, time-consuming, and very error-prone. So what we have is we have a couple of facts here that are going to help us out. Now, first of all, this is the fact that's going to help us out directly right here. There's 37 of these guys, okay? There's 37 primes between 600 and 850, which is the constraint on the summation, okay, on the summation. Let me come down there. Yeah, we do have a summation here, and we're summing up through all the primes that are strictly greater than 600, strictly less than 850. Neither one of those are primes, so that's really unnecessary. But so we're given a priori or in advance that there's 37 primes satisfying that condition. Now we also have a nice little fact that requires some proof. I'm not going to prove it. I proved it in another video. But it turns out any prime greater than or equal to 5, when you square it and subtract 1, you're going to get a multiple of 24. You can see it clearly with 5 squared, right? 49 squared would be another example. 7 squared, right, equals 49. But notice that 49 is congruent to 1 mod 24. And y'all, if you haven't seen congruence, it's really fairly simple. It looks kind of strange. It's a triple equal sign. But 49 is congruent to 1. Notice the congruent symbol here, modulo 24, because when you subtract 1 from 49, you get 48. And 48 is equal to 2 times 24. So that's an example. And 5 is easy. 5 squared minus 1 is just 24 right out, right? Try it for some others, though. It's a provable result. You can prove it by checking out the case p squared is congruent to 3. That's easy. It's easy to show that p squared is congruent to 1 mod 3, and it's not much harder to show that p squared is congruent to 1 mod 8. And then if it's congruent to both of those, then that means it's congruent to 24, the product of two relatively prime moduli. Okay, so we're going to use these two facts, and the result is really pretty fast at this point. Okay, so we already know there's 37 of these primes, so we're going to get that this is this summation here. Each one of these p squareds is congruent to 1, right? So we can just simply write 37, the sum of 37 ones, right? But notice that we're supposed to write it as a member of the reduced residue system. So we have to write down, we have to note that this would be congruent to 13. Yeah, that's the answer to the problem. X, I guess I'll write it right up here, x equals 13 also, but x equals 13 turns out to be the solution we're looking for. And any other number congruent to it modulo 24 would be another solution, just not, you know, in the reduced residue system. So x equals 13. And y'all, if you're interested in seeing the proof of this, it's really kind of cool. Part of it's based on the fact that any odd number is congruent to 8 mod 24, and a prime is odd. You know, we're taking the prime to be an odd prime, that we're not dealing with 3, we're not dealing with 2, right? And so then showing that p squared is congruent to 1 mod 3 is very straightforward, okay? So it's this proof isn't hard. This part here is very time consuming. I would think that if somebody was going to give this as a competition problem, they would tell the competitors that this was true. It'd be too much trouble to go through and check, you know, without the aid of technology. So this is a necessary given condition right here, in my opinion. This right here might be something practice competitors would know about. But in any event, we're done. 13 is the answer. Hope you enjoy.